and happy one. Where are the others?
I think they will be coming. I already see Susmita is coming. Happy birthday.
Thank you.
Wish you a happy birthday and
Thank you
many
very
more
much,
happy
ma'am.
returns
Okay.
of the
You
day.
to talk and I will make other arrangements.
Yes,
Okay.
go ahead. Yeah, let's sit down. How are you, Sushmita?
Fine, ma'am.
How is it going?
Yeah, it's going great. I just finished class and came.
Oh, very good.
He had invited for a get together, so okay.
Yeah, let's enjoy
Yeah,
among the students. And they'll have to.
he's here.
Oh, yes, Kuntal. Come. Oh, that's very interesting. You have a rectangular cake and a rectangular icing on top of it.
What is interesting about the shape, ma'am? It's the ingredients that make it tasty.
I don't deny it, but it is interesting. Okay, how much is Sushmita's share?
Of course, half of the cake and half of the icing.
Okay, so I will take it only if you can cut it into two equal halves by a single straight line.
Oh, you have proposed a very interesting problem, Sushmita.
Is it?
Yeah, can you do that?
I don't know. Maybe we have to cleverly use the idea of rectangle.
Oh.
If it had one rectangle, then we could have done it. We could have joined the midpoint of opposite side and we could have cut along that line.
I had proposed this problem earlier to a group of students in one of my lectures. Here is my pen drive. You are very lucky, so I can show you the details here.
On the left.
Yeah, on the laptop. Give me your laptop, Kuntal. Yeah. Yeah. So the problem is you have a bigger rectangle and which represents your cake and a smaller rectangle which represents your icing.
Okay.
So Sushmita would like to have her share which was proposed by you, provided you have a single line cutting the bigger rectangle and the smaller rectangle. So the problem is as follows. Can you cut a rectangle by a single straight line such that each side contains exactly half of the cake and half of the icing as well? Is the problem clear to you now?
Yes.
So can you see it here?
Yeah.
Okay.
So what about the orientation of the icing? Can it be anywhere on the top of the rectangle? Means the cake?
Yes, of course. The icing can be located anywhere on the top surface and its orientation can be anything. So, you understood the question.
Yes, ma'am, we have understood the problem. Actually, we have to use the idea of rectangle, the geometry of rectangle to solve this problem. If it was just one rectangle, then we could have joined the midpoint of the opposite side and we could have cut it along that line. It would bisect the area into equal halves.
Yes, you are right.
I think the diagonal will also work.
Is that the only solution to the problem? Do you have more such straight lines?
I feel
Cutting
like,
the
I feel
area?
like there will be many lines.
Let us see. Suppose say I consider a straight line A2C2. You can look at this picture. I have the details with me. So if you have a line A2C2 passing through the center O of the rectangle ABCD, then the area to the left of the line A2C2 is K1. To the right of the line is K2. And the area OC1C2 of the triangle is X and that of OA1A2 is Y. And we see that X and Y are congruent triangles
Yeah.
and therefore they have equal area.
Yeah.
So let us now compute the area K1. So K1 is K by 2 where K is the area of the rectangle ABCD minus X plus Y, but X is equal to Y and therefore K1 will be equal to K by 2 and therefore K2, which is on the other side of the straight line, is K minus K1, so that will be K by 2.
Yeah.
So a straight line which passes through the center of a rectangle bisects the area into equal halves. So is that clear?
Yeah.
Yes, ma'am.
So any line passing through the center of the rectangle will divide it into two equal areas.
Exactly.
Maybe there are other lines also.
Let us check. Let's take a straight line not passing through the center. Suppose this line B1, F1, A3 cuts the horizontal line through the center at F1. Let EF be the vertical at F1. Then you see that K is the area of the rectangle ABCD. K1 is the area to the left of the straight line and K2 the area to the right of the straight line, and X and Y are areas of the two triangles A3F F1, EF1 B1, which are congruent triangles and they have equal areas.
Yeah.
So let us denote by Z the area A, E, F, D. Then Z has an area which is bigger than K by 2.
Yes.
So let's now compute the area K1. K1 will be Z minus X plus Y,
Yeah.
which is Z because X and Y are equal.
Yes.
And that is greater than K by 2. We already have noted that.
Yeah.
So K1 is bigger than K by 2. So naturally K2, which is K minus K1, will be less than K by 2.
Yeah.
So therefore, the only straight lines bisecting the area of the rectangle are the lines through the center of the rectangle. These are the only straight lines bisecting the area which pass through the center of the rectangle.
Yeah.
I think I can solve now the initial problem.
Oh, what is it? How are you going to do it?
But how do we do it simultaneously for two rectangles?
Yes, yes. See, any line passing through the center, cut it into equal halves.
Yes.
Now take the center of the cake
Okay.
as well as center of the icing
Oh.
and join that line.
Okay.
That will divide the icing as well as the cake into equal halves.
Yeah, perfectly right. So if a bigger rectangle has to be cut into equal halves, the line has to pass through the center of the bigger rectangle.
Yes.
And a smaller rectangle has to be cut into two equal halves. So the straight line has to pass through the center of the smaller rectangle. And therefore, the line joining the centers of the bigger rectangle and the smaller rectangle will do the job. So, straight line passing through the center of both the rectangles will do the job. Is that right?
Yeah.
So,
now I can satisfy your condition.
Uh.
Is it okay?
Yes, okay. We can have it when the others come.
oh, that's fine.
Okay. But ma'am, let me ask you, what will happen if we change the shape? Maybe for the triangle if we have.
Oh, you mean to say that you are given a triangle and you have to cut it by a straight line,
Yes.
dividing the triangle into two equal
Yes, ma'am.
parts of equal areas?
Yes,
Is that what you meant? Okay, I will continue to show you. So, I understand that this is your problem, namely you have a triangle and you want a line to cut any two sides of a triangle such that it divides the triangle into two equal parts of equal areas. Is that right?
Yes ma'am, that's what I was asking.
But we don't have a point symmetry for a triangle as we had in a rectangle.
But I think that median always bisect the area into two equal halves.
Yes, you are right. Let us see. So, take a triangle ABC and let a straight line cut the sides AB and AC at P and Q respectively. So, for our problem, if the straight line PQ does the job, then we must have area of triangle APQ to be equal to half the area of the triangle ABC. So, do you see any conditions on the points P and Q?
I think
Wha-
they will depend on the length of AB and AC.
Okay, what are their positions on the sides AB and AC? So, let us just take AP to be lambda times AB and AQ to be mu times AC. Do you get it now?
Yes, I think I get it and I will solve it in my notebook and show you.
Yeah, let us see what you do.
Do you have a pen?
Yeah.
Thank you. So now we have the triangle ABC and we have P and Q,
Yeah,
and we also have that AP is equal to lambda times AB
Yes.
And AQ is equal to mu times AC.
Yes.
Since we need area of triangle APQ to be half the area of triangle ABC,
Yes.
we have this equation, and hence now area of triangle APQ will be half into lambda times AB into PQ into sine angle PAQ divided by half into lambda times or half into AB into AC into sine angle BAC.
Yeah.
I
Okay,
think
yeah,
it
this
will
is
be
not
AQ.
PQ. Yeah, this will be AQ, that is
Yeah.
mu AC. So this should be equal to half, which says that lambda into mu, because all this will cancel off.
Yeah.
So we have lambda into mu should be equal to half. This
Yes.
is the required condition.
Exactly. So you see the restrictions on lambda and mu.
So lambda mu should be half.
Yeah. So lambda must be less than or equal to 1 and mu must be less than or equal to 1
Yeah.
because AP is lambda AB
Yeah.
and AQ is mu AC.
Yes.
In addition, you have just now shown that lambda mu should be equal to half,
Yes.
and therefore you can see the condition imposed by these two, namely you must have half less than or equal to lambda less than or equal to 1
Yes.
and mu is such that half less than or equal to mu less than or equal to 1
Yes.
with lambda mu equal to half.
Yes.
So let us see in this simulation what happens when mu is 1, Q coincides with the point C, which is the vertex of the triangle.
Yes.
Since lambda mu is half, AP will be half of AB
Yes.
and therefore P will be the midpoint of AB.
So it's a median.
So CP becomes a median, and your earlier observation is seen here. And as Q moves along the side CA such that mu decreases to half from 1, P will move towards B, and so lambda will increase from half to 1.
Yes.
So do you see the animations?
Yeah.
This straight line keeps on changing, and you have all these straight lines, namely infinitely many of them, which bisect the area of the triangle. And the observation that you made earlier, that each of the three medians bisect the area of the triangle, is clear from here.
Yes.
It's actually a special case of our.
Yeah, it's a special case of our observation when lambda is 1, mu is half, or mu equal to 1 and lambda is equal to half.
So this tells us there are infinitely many straight lines that bisect the area of the triangle ABC.
Yeah, we have come for a birthday party, but we have discussed very interesting problems. So we have come a long way, namely a good distance from where we had started. That's
Yes.
very interesting. I really enjoyed this conversation. Okay, let us relax.
Something new also.
Okay, that's good. Let us relax and enjoy the surrounding and this evening.
I see lots of trees and greens in this vast expanse.
Oh, something else comes to my mind. Imagine that you have a very big garden.
That's
Okay.
nice even to imagine.
Okay, that's fine. Enjoy. But I'm tempted to pose another problem to you. Is that okay?
Yeah, sure, ma'am.
Okay, let us assume for simplicity that your garden is bounded by a closed convex curve.
Okay, we know what a closed curve is, but what is a convex curve?
Yeah, a convex curve in a plane is a curve that lies on one side of each and every one of its tangent lines. You can see it here. A circle, an ellipse or parabolas, rectangle, all these are convex curves in a plane.
Okay.
On the other hand, if you take a sine curve, then it's not a convex curve as it is clear from here.
Ma'am, I think every regular polygon will also be a convex.
Yes. So let me make my problem simpler. I will come back to concave curves later. Suppose say you have a garden which has its boundary to be a circle. And imagine very tall vertical trees which are located in an arbitrary manner in that circular garden. And let us also assume that we are walking through your circular garden. All right, what is it that I want? Can you construct a pathway along which we can walk through your circular garden such that you have equal number of trees on either side of the pathway in which we are moving? Do you understand the problem?
Yes, ma'am, we have understood. But why do you say that tall vertical trees?
Oh, that's just to make sure that the trees look like vertical poles. In other words, I'll formulate the problem this way. The problem is just the same as the following. In a circular region, you have a set S of points which are located arbitrarily at random, or which are chosen at random from the set S of points in a circular region. Then my question is, find a straight line across the circle so that there are equal number of points on either side of this straight line. That's what my question. So, do you see in this picture?
Yes.
Yes.
So, I have points over here located here which resemble the vertical tall trees in the circular garden, and I want you to give me a straight line path such that as we walk through the garden along this path, we have equal number of trees on either side of our pathway.
But this obviously depends on the distribution of the trees in the garden.
But nothing is known about the distribution of the trees in the garden.
Okay.
I still want you to solve this problem.
If they lie in a same straight line, then we can do.
Yeah, of course, of course.
But, for a arbitrary fashion, maybe we have to think about it.
Okay, I'll give you a clue. Take a point O and a ray originating from O such that the infinite ray fully lies outside the circular area occupied by the circular garden. And you fix an initial position for the ray, call it OA. I will show it to you in my figure.
Okay.
So, the step 1 in our construction of the path is this. What did I say? I said take a point O and then originating from O take a ray so that this infinite ray OA lies completely outside the circular garden. Is it okay?
I see that circle is lying in one side of that ray.
Exactly.
Now I can tell you what to do. We just have to start rotating the ray about O, say in the anti-clockwise direction. Initially the ray does not cut the circle, but as we keep rotating it, it meets the circle at some point of time.
Yeah, again I have the animation here. You can see this is an initial ray. So, as the ray starts sweeping, at one position it will meet the circle.
Yeah.
That's what Sushmita had told us. So, at this stage I would like to make a following suggestion.
Okay.
You choose the initial position OA of the ray in such a way that as the angle of rotation varies from 0 to 90 degrees, the ray completely sweeps the entire circular garden.
Okay.
So, with this suggestion, see whether you can give me a solution.
Okay, yes. Now we can just start counting the number of trees. Like when we continuously sweep through the circular area, we can start counting, and we can stop when we reach 500. And before we go to 501, we can take the path in between these two rays, and that will be the required path.
Yeah,
Yeah, that's a brilliant solution, I think.
yeah, it is a good idea, but it lacks clarity and it looks incomplete to me. This is typically an engineer's first plausible solution.
So is my argument wrong?
There is something missing in your statement. I have a question to you. What if at a particular position while sweeping, say at theta, the ray passes through more than one tree?
Oh,
Okay.
yes. It's
Yes.
a good question. But before that, let me ask you, at most how many straight line will be there joining any two trees in the garden?
Suppose there are 1000 trees in the garden, then there will be 1000 C2 lines joining any two trees.
Okay, so let us fix our number of trees to be 1000 in that garden.
Okay.
The number of lines, namely 1000 C2 is finite.
Yes.
But there are infinitely many straight lines through O. So we may choose our initial ray to be 1 such that O is not on any of those 1000 C2 lines.
Yes.
And our OA is different from any of those 1000 C2 lines. Then that answers my question. What
Yes.
was my question? What if at a particular position, as the ray sweeps, say at theta, the ray passes through more than one tree?
Yes.
Because of our choice now, for no value of theta between 0 and 90 degrees,
Yes.
the ray passes through more than one tree.
Yes.
Because our initial choice of OA is such that the origin O is not on any one of those 1000 C2 lines, and OA is different from those lines which we have avoided.
Yes.
So at every stage, as the ray sweeps through the circular garden, the ray passes through at most one tree. Is that okay?
Yes,
Yes.
ma'am. A very brainy choice of that initial point, and we solved this problem.
Okay, Shushmita, complete the solution.
Okay. So when we sweep through the circular region, suppose at theta is equal to alpha, the ray passes through the 500th tree, and at theta is equal to alpha plus beta, it passes through the 501st tree. Then choosing theta is equal to alpha plus beta by 2 gives us the path. The ray through theta is equal to alpha plus beta by 2 is the required path.
Yes, you are perfectly correct. So let us see, this is what is happening. So we started with an initial ray OA. We took the ray position O and the ray originating from O, namely the ray OA, to be such that as OA rotates through 90 degrees, it sweeps through the entire circular garden.
Yes.
And then as it rotates, initially it cuts the circular boundary, and then it sweeps, and you observe that at any position the ray does not pass through more than one tree.
Yes.
And you see the blue line in my figure,
Yes.
that's where you have your alpha plus beta by 2 given by theta is equal to alpha plus beta by 2. Which is going to be the straight line path that we should take through your garden, so that we have 500 trees on either side of our path.
Yes, ma'am. It's a very good solution.
Yes, it's a very interesting one.
Actually, I think that it happens because we continuously moved from theta 0 to 90 degree. It continuously swept through that garden, missing without any point of that garden.
Exactly. So you see the power of continuity in this problem.
So can you explain mathematically what continuity means?
Yes, sure. I will explain to you when we meet next time.
Okay.
And now it's time for us
Yeah.
to enjoy our cake.
I see others are also coming.
Oh, that's
Yeah.
nice. Hi.
Okay.
Okay.
So, yes.
Happy birthday.
Thank you. Let me cut it into exactly 2 halves. So, this is the center of this, and this is the center of this. So,
But why do you want to do all that? Why can't you simply cut the cake?
actually, ma'am was explaining a problem to us, which I will tell you later. Okay? So, yes, half.
That's nice. We have solved the problem with which we started.
Now, eating half of this cake, I am going to become fat.